All right, so picking up where we were, so we had decided we had to calculate the net torque around point P. So that's going to be the torque from gravity plus the torque from the tension, right? And I don't need to worry about the torque from the hinge because it's 0, because our lever arm there is 0, right? Clear? All right, so let's do this. Because we're sort of new with this, let's, instead of just writing out one big equation, let's split this up. So let's first of all write an expression for the torque by gravity. So the torque from gravity is the force of gravity times the length of the lever arm times something with some trig, right? Okay? So there are a couple of ways of doing this. Remember, in general, to find torque, kind of where we landed the other day was we decided that there are 3 ways you could calculate torque. You could calculate force times distance and ensure that you use the component of the force that's perpendicular to your lever arm. To me, that doesn't make a ton of sense in this problem because it would mean taking this vertical force and splitting it up into components, right? So your perpendicular component would be kind of this way, right? Do you guys see that? Yeah. All right, so that doesn't make a ton of sense. Option 2 was to multiply the force by the perpendicular component of the lever arm. To me, that makes a little bit more sense, right? Because in this problem, our lever arm is this beam, right? And it technically is a vector, so really there's a little arrowhead at the end of it. Okay? So what I want is the component of that lever arm, that blue lever arm I just highlighted, that's perpendicular to the force, right? So isn't that just this guy here? Right? Now, I didn't tell you how long the lever arm was, right? I didn't tell you how long that rod was, so we should give that a name. L? Great. Let's use L. Great. Cool? So that means that the perpendicular component of that, isn't that just L times the cosine of theta? Does anybody not see that? Right? That would give me this horizontal distance, L cosine theta, right? So I think that the torque from gravity is going to be L times the cosine of 20 degrees. So that's my D. And then times the force of gravity, which is 400 newtons, right? So there's the torque from gravity. Are there questions on how I calculated that? Good? Okay. Also acceptable. So here's the third way of finding torque. If all of this component business is confusing to you, the safe bet, the way that will always work, although it is often more work, is to do this. But what's theta? Not numerically, but conceptually. Like in words, what does theta mean?
Between the arm and the force.
The angle between the force and your lever arm. So in this problem, our theta would be 70 degrees, right? So if you prefer, you can just do 400 times L times the sine of 70, and you're done. Okay? And frequently, that's the easiest way.
Wait.
Nope, because this angle here would be, you're ahead of me a step, Kate. The other angle is 65. This angle here would be 70, right?
If we were to do that, what would distance be?
It's the same thing, L.
And we know that.
Yeah, well, we've decided to call it L.
Oh, cool. All right.
All right, everybody good? Okay, and remember, cosine of 20 and sine of 70 are the same, so good? All right, so let's just neaten this up. So I guess that's, I don't know, yeah, that's fine. Okay, so there's our torque from gravity. Positive or negative, you guys? Pivot point, force, is that clockwise or counterclockwise? Clockwise, so this is a negative torque, right? Oops. Negative torque. Cool? All right, now we got to do the torque from the tension. So this one's a little bit more complicated. And honestly, because both your lever arm and your force are at weird angles, I would probably just jump straight to this. Okay? Here's what you can't do. And Sebo, I'm worried this is what you did. And
No, I was totally doing that.
Okay. All right. Just one thing you can't do is you can't find this horizontal distance and the vertical component of this force and multiplying. Because that only accounts for part of the torque. Okay, because then there's another torque that goes, I don't want to get into it. So if you've got a lever arm and a force that are both at weird angles, then just use this. And better safe than sorry. Follow? Okay, so for us, we're trying to find the force of tension. Our lever arm is L times the sine of, what's this angle here between my lever arm and my force? 65, right? Follow? All right, and then we can fairly safely assume that that torque is going to be counterclockwise, but let's not gamble on that. Let's let the math do the work for us. Sarah.
Now, this is going to be a really dumb question.
You're okay.
Where'd you get 65?
Gotcha. Let me clean up my. I got to erase some of the drawing here. All right. So we're looking for the angle between between this blue lever arm and this pink force, right?
Right.
And it gives you that this is 45 degrees,
Oh,
and then this little bit here is 20. Cool?
Yep, thank you.
Everybody good with that? All right, cool. All right, so let's write it out then. So this black equation, the net torque needs to be what, you guys? What's the net torque? 0 equals the torque from gravity, which is negative L cosine 20 times 400 plus Ft times L times sine of 65, and solve it. So notice when you do this, you get the force of tension times L times the sine of 65 equals L cosine 20 times 400. Cool. So the L's cancel, right? But notice, here, at this point, there's a point where you need to pause that might not be obvious. So this represents the torque from tension. And notice it's going to give me a positive thing, right? So that's telling me that my tension has to provide a positive torque, which tells me the direction the tension has to be pulling. Okay? Like, what if this had been a beam instead of a rope? Isn't it possible it could be pushing? Okay? But then this is telling us that it can't be. It's got to be pulling in a way that creates a positive torque. In other words, counterclockwise. Follow? Any problems? Okay, so find that tension force and you end up getting 414.73 newtons. All right, everybody good?
Yep.
All right. So now what we can do is now we can take that force of tension and split it up into a horizontal and a vertical component, and now use net force X equals 0 and net force Y equals 0. Follow? All right. I know, right? It's a long problem. All right, so if you do that, here's what you get. So algebra and trig gives that our force of tension in the x direction is negative 293.26 newtons, and the force of tension in the y direction is positive 293.26 newtons. Right? Because it's a 45-degree angle, so your x component has to equal your y component. Everybody good? All right. So then, if you use this, the net force in the x direction is 0, tells us that the force of the hinge in the x direction has got to be positive 293.26. Everybody follow what I did there? Right, just basically, we knew the tension in the x direction, we got to find the hinge in the x direction. Follow? Too fast, or are we good? All right, and then similarly, ooh, I said it right. This equation, now we know our FG, we know our force of tension in the y direction, so we can find our force of hinge in the y direction. And so it turns out that the force of the hinge in the y direction is 106.7 newtons. Cool? All right. So there's another example like this in the packet. It's solved very similarly. I need to find a synonym for that, so I don't have to say that. All right. So I'm not going to go through it because we're tight on time, and I want to make sure we get to a pulley problem. So where did I put it? Okay. So jump back to the problem that says a 6-meter board, blah, 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 blah. Is it? Okay, great. I think I rearranged my slides. All right. So first of all, you got to make a drawing. So we've got a board that's 6 meters long. It's propped up to form a ramp onto a platform that's 2.5 meters tall. The top of the board, and it gives you the mass of the board, extends 2 meters past the corner of the platform. So it sounds like you've got a platform that's 2.5 meters tall. We've got a board that's 5 meters long, but I'm sorry, 6 meters long, but it extends 1 meter past the corner. So like that. So this is 1 meter, and that would mean then that this is 5 meters. Follow? All right, so there's my drawing with all of my distances labeled. The mass is 30. Oh, I forgot to put my units in there, kilograms. Oh, shoot, I didn't explicitly say that it was uniform. Did I put that in yours by any chance? Okay, let's assume that it's uniform. That's my bad. So, assuming that it's uniform, that's going to tell you where your center of mass is, right? So 3 meters up. So that's going to give us a force of gravity of 30 times 9.8, which is 294 newtons. Oh, yeah, we can make it negative if you want. Everybody good?
So far.
All right. Depending on how you count, there are 2 or 3 more forces on this thing. So, normal force. There's actually normal force occurring at 2 points, isn't there?
Yeah.
There's the normal force from the floor and the normal force from the platform. So here's the main thing I wanted to go over. So there's a normal force from this platform pushing on the board over here somewhere, right? Not at all obvious, but I want to make sure you guys get this. So like this is like a trick that you should know. What direction do you think the normal force acts in? Can you point for me? Does it point straight up? Does it point sideways? What do you think? Yeah, isn't it going to be perpendicular to the surface? All right, realizing that requires Newton's third law, actually. Okay, the idea is the force of the board pushing the corner has to be perpendicular to the board, right? Which then means that the force of the corner pushing the board has to be also perpendicular to the board, right? So instead of calling that normal force, let's call that FC as in force of corner. And notice we don't know how much that force is.
Is that force like at a 45-degree angle perfectly?
I don't know because I haven't found any angles yet, but I do know that this angle is 90 degrees.
Well, just because it's
I don't think so.
relative to the ground, wouldn't it have to be?
I think it's 6.
Oh, wait, no, because it's like, it depends on how the platform's laying on there.
Yeah, exactly. Depends on how steep the board is. I think this angle ends up being 30 degrees.
Yeah,
'Cause it's
sorry,
a-
I made a hasty generalization.
All right, everybody good up to there? All right, So notice, this is important. This actually ends up being very similar to the one we just did. What's got to be going on down here? You got to have another normal force from the floor.
But that's straight.
Why is that one straight up?
Because the point of contact is like directly going.
Because at the point of contact, you're touching a horizontal surface. And remember, by definition, normal means perpendicular. So it's got to be perpendicular to the surface. Just like this one is perpendicular to the surface of the ramp. Cool?
Yeah.
All right, and then there's got to be one other force. Remember, the problem tells you this point is frictionless. So think about what would happen. Wouldn't the ramp slide down? So there's got to be friction pointing this way, right? Cool? All right, and notice the corner's pushing to the left, so friction has to be pushing to the right. Cool? Questions, issues, concerns? All right, so there's your drawing. The setup for this one is actually very, very similar to the one we just did. All right? Yes?
What would you make your pivot point?
Tell you what. See if you guys can figure it out. Turn to like whoever's within 3 feet of you and see if you can figure out where your pivot point is. Yes?
On this corner, is there friction? Is this frictionless?
This corner, yeah. If the corner of the platform is frictionless. No, that's okay, that's okay.
Alright, let's do this.
All right, now I will say, you guys, remember, we always have 3 equations to go on. Net force in the x direction is 0, net force in the y direction is 0, and net torque around any pivot point is 0. If you can, where should you start? Like, which of those equations is simplest? Wouldn't net force be easier because you don't need to worry about your distances?
Oh, right.
Right? Okay, so if you can use one of the net force equations first, that's where I always start. Okay? Then, if those fail, which they usually do, then you go to your tension. Okay? And so Daniel's question is a great one. Where do we pick the pivot point? So in simple terms, what's our goal behind picking the pivot point?
Eliminate force.
Eliminate at least one of the forces. How many unknown forces have we got here, you guys? I count 3.
So we can get rid of
We don't know the force of the corner, we don't know this normal force, and we don't know this force of friction. So where do you pick your pivot point? Adam, what do you got? Down here, right? At the bottom, because that will eliminate those 2 forces, just like we eliminated the force of the hinge in the last one. Okay?
So why would you write the force of static friction as normal force times coefficient?
Oh, you could do that and then do a system? Oh, 100%. Yeah. That's going to get ugly real quick, though, but you can do it that way. Yes?
Is there friction on the corner?
No. No friction on the corner. If the corner of the platform is frictionless.
Oh, didn't see that.
That's okay, you're not the first. Yes?
So how is that a pivot?
So remember, when you choose, pivot point doesn't always mean fulcrum. Do you know what I mean? Like on a teeter-totter, you always think, oh, this is the pivot point, right? But once it's balanced, it's not pivoting around any point. Okay, that's sort of like, that's what's at the crux of this whole net torque lesson, is that you can pick any point you want to be the pivot point. Okay? So to help justify it, hypothetically, suppose that this corner suddenly just disappeared. What would the board do? It would pivot around that point, right? Does that make sense? Does that help at all?
Yeah. So it's like still.
It doesn't make sense how it's sliding? Is that what you said? Say it one more time, I'm sorry.
The pivot point is like suddenly sliding back.
Well, but since it's in equilibrium, it's not going to slide. You see what I mean? If it wasn't in equilibrium, so this is a thing that I don't think it's ever come up in any of the problems. If it's not in equilibrium, then you have to choose the center of mass as your pivot point. and it gets ugly. Cool? All right, questions, you guys? Okay. I wanted to do a pulley example. We very clearly don't have time. So, tell you what. Tonight I'd like you guys to at least get started on the 13 homework assignment. If you get to a pulley problem, just skip it. Okay? Other than that, you ought to be able to solve everything we've done. Okay? I'm not going to make anything specifically due tomorrow. Probably tomorrow I'll finish up the notes and then give you guys time to work. Okay? And then Monday I'll make some chunk of it due. Okay? And we'll make Monday a Q&A day, and then we'll do one more Q&A day somewhere in there. Probably Tuesday, probably test Wednesday, and then Thursday will be, I guess, one day of gravitation notes and stuff. All right?
Yep.
Okie dokie. I'm debating doing, because there's only 2 notes for gravitation, I'm debating doing videos again like I did for whatever chapter that was forever ago. Was that manageable?
Yeah.
Okay, so I may do something like that. I'm trying to see if I can get my things together. I didn't want to say that.
One of them is
This is what I was worried Sevo had done. So right direction of this force, your force is already perpendicular to your lever. So this torque is literally the force and its distance. The harder one is finding the torque of gravity. Because your gravity is not perpendicular to your lever. So, and then we've seen a few different ways to deal with that. In other words, I would not split something into because if you split something into components, your horizontal component is going to provide a torque this way, right? Because it's pulling this way, right? Your vertical component produces another torque. So you have to find the torque from the horizontal component. So you're better to just go straight from, well, the torque's already on the table. You put it when you do the net force equation, there is no pivot. Do you see what I mean? So yeah, I see now what you were saying. I got it. Yeah, so picking your pivot point here helps you for the torque equations, but not for the force equations.
Yeah. So you find your forces and then take it to the point, that eliminates some unknown forces and push it.
Unless you're able to, so I always start with the net force equals 0 equations.
Yeah.
But in this one, they don't help us any, because we have 2 horizontal forces and we don't know either of them. And we have 3 vertical forces, but we only know gravity.
Yeah.
So again, that doesn't help us. Hypothetically, suppose we had known this normal force. Okay? Sorry, Dan, 2 more seconds.
No, you're fine. I'm just.
So what I would do, if we knew this normal force, I would say, oh, cool, well, I know my normal force. I know my gravity, so I can find the vertical component of this force, because all 3 of those vertical forces have to add to 0.
And then you don't need to take it.
And then you don't even need to worry about the vertical force.
Yeah.
Usually when that happens is when there's a missing distance.
Okay.
Do you know what I mean? Where like it might say, like, where do we need to put this other force to put it in equilibrium? Usually in those problems, you start with the net force equation.
Okay.
Follow?
Yep. Thank you.
Sorry, what's up?
Really quick, it's not important, but if this is like a true corner, how can we say that that's perpendicular? This doesn't a corner not have?
It's perpendicular to the board, not to.
Oh. Oh. I mean, okay, duh. That's-
Well,
that's
not
really-
duh. That's not obvious. But like if you flip it this way,
Yeah.
if you think about, okay, here's my board, putting a force on the corner,
Okay. Yeah.
that force has to be perpendicular to the board, right?
Okay. Yeah.
And therefore, by Newton's third law, the other force also has to be.
Okay.
Right, because they're
It's just
equal and
weird to think
opposite.
of something laying perfectly flat on a corner, because the corner doesn't have,
Right.
but the board itself has this slope, so, okay.
Yeah.
Because, you know, I mean, I was thinking like in calc, you can't take a derivative of something at that.
I gotcha.
Yeah. All right, thank you.
Yeah. Hey, Dan?